So we have established so far, we have extrema, that is extreme values that are local max and mins or global max or mins. That wonderful example that I keep drawing, where we see this function act like this. That's not a good version of it. If our function acts like this, then we have our global minimum right there. And then on the other side, we have just our local maximum and a local minimum right there. Well, then we use the idea of a critical value, noticing, well, all of our max and mins happen when the tangent line is flat. Well, that's when the derivative is zero. So we say, okay, let's take our function, set it equal to zero, and then say C, whatever that solution is our critical value. That point in the original function being our critical point, and that we notice most of the time is a local max or min, and may even turn out to be global as well. Well, then we develop our first derivative test that if C is a critical value for a function, then if that derivative changes from positive to negative at C, then f of C is a local max. If the derivative changes from negative to positive at C, then f of C is the local min. And if f prime does not change sign at C, then f of C is nothing. It is no longer relevant. And that last picture that we drew is the example of that last case. An instance where our derivative is zero right at this point, a flat tangent line, but it turns out to neither be a local minimum or maximum. It is nothing. It is not an extreme value at all. Okay, well, now we're going to talk about our second derivative. So first of all, let's think for a second about our second derivative. Now, if we can kind of recall, it is just the derivative of the derivative. And let me actually emphasize that what we end up caring about the most is our second derivative test, where again, we start out making sure that C is a critical value. Well, so here we're going to get three cases as well. Though I suppose I'm writing this right. So, and these are going to be essentially consequences of our first derivative test. So first of all, if f prime changes from positive to negative, so in this first case, if f prime changes from positive to negative, then, well, the derivative of a function, sorry. If f prime changes from positive to negative, then we are going from a positive number to a negative, so we must be decreasing. Well, if a function is decreasing, then its derivative must be negative. So if f prime is decreasing, then f double prime is negative or less than zero. Except we're not talking about at any value, we're talking about at our critical value C. So if f double prime of C is less than zero, then we are in the case of our first derivative test. So f of C is a local max. Well, now in the second case of our first derivative test, if f prime changes from negative to positive, then it is increasing, which means its derivative must be positive. So the derivative of the derivative being positive puts us in that case. So I'll write positive just as greater than 0. Then f of c is, in that case there, a local minimum. And then in the third case, if actually for this second derivative test, we don't really emphasize the third case there when it equals 0. And that ends up being a totally separate kind of definition that we end up bringing up on our own. So these are essentially the tests that we like to look for and remember, and that we will refer to a lot. So this is essentially all of the information that we want to know whenever we're looking for maximum and minimum values. This is our guide to max and mins and finding them. So let's take all of that information and try and find some maximum and minimum values. So let's clear all of this out. Is there a button to do that? Oh my gosh, there is. Incredible. Okay, so let's say our function f of x is x to the second minus 1, maybe something very small and neat. So let's say we are asked to find and classify all extrema or extreme values. So first of all, what we want to know first, step 1, is we want to find critical values. And then step 2, once we have them, we want to classify as min or max, or that really weird, lame case where it turned out to be neither. So first of all, in order to find our critical values, we said our critical values is where the derivative equals 0. So let's find the derivative of our function. So if f is x squared minus 1, the derivative of our constant would just be 0. And the derivative of x squared is 2x. So it'd be 2x plus 0. So I'm going to go ahead and just write that as 2x. I want to try and write that better as 2x. Okay, here we go. So the derivative is 2x. Well, let's set this equal to 0 to try and find critical values. Well, if 2x is equal to 0, to solve for x, I can divide both sides by 2, and this is 0 over 2, which is just 0. So we have critical value at x equals 0. Well, now we want to classify this as a max or min, or if it turns out to be neither. So the good way of doing this, I would say, is the second derivative test. So we remember if our second derivative is positive, we are a minimum, and if our second derivative at that point is negative, then we are a maximum. So if f prime is x squared, then f double prime, our second derivative, sorry, if f prime is 2x, then f double prime, the derivative of f prime, derivative, the second derivative being the derivative of our first derivative. We look at our derivative and we take the derivative of that. The derivative of 2x is just 2. Well, f double prime, when I plug in 0 to this function, this is still just 2. So f double prime of 0 is positive. Thus, f of 0 is a local. We said if it's positive, then it is a local minimum. Well, this is certainly true, but it doesn't really tell me enough. I want to know what that number actually is, right? If someone said, what was the highest value that this stock was worth? And you said, that was the value at 5 days, and they'd say, I didn't say when, I said, what was the highest value of the stock? We want to know the output. We want to know exactly what this number is, f of 0. So well, I'll keep that there. We want to plug 0 into our function, our original function. Well, 0 squared minus 1. In this case is 0 times 0, so 0 minus 1, which 0 minus 1 is -1. So we would really say, thus, -1 is a local min, and we would like to say at 0. And maybe we even specify at x equals 0. But as long as you include kind of all that information there, maybe you say f of 0 is a local min and f of 0 is equal to -1. That's really communicating all the information that you need to, right? But this is the process for this kind of question. We take the derivative, we set it equal to 0, we classify whether that um, critical value is a maximum, a minimum, or neither. And then we kind of give a little bit of a sentence saying, well, though then we have this local minimum or local max of whatever at whatever. So we have a local minimum of -1 at 0. Now, obviously, this is not a model. There's not a description here. But if there was a description here, we would kind of want to say what those means, which is a moment where we interpret those answers, which is something from earlier. So if my output was -1 and this was something with dollars, well, it'd be sad to have -$1. I guess that's debt. But this would tell us that at, if our inputs are time, maybe a time equals 0, we have a minimum of -$1. So again, if this is a model, we'd want to interpret this, which just looks like the same stuff as before. So there's kind of just adding layering network on top of what we're already doing here. So this is how we find and classify our extreme values. There is another way of doing this, and that is entirely with our calculator. So I'm going to draw what happens on our calculator, and hopefully you can look at your own calculator and go from there. So let's go ahead and continue working with this function, x squared minus 1. So there's not an easy way to erase a lot of things at once, unless you're smart and just erase everything at once and then rewrite this at the top. Anyway, so let's use our calculator to try and find this min or max value. So what we're going to do is say y1 of x, or we go to that list and we set y1 equal to x squared minus 1. Let's type that into our calculator. Then we can graph it. And we kind of mess with our window a little bit to make sure it's a good picture of the graph. And it turns out that the graph of our function looks essentially like this. Well, then we can hit the second button and then trace to go to a menu with max and min on it. So once we graph it and we make sure that our graph, our picture of the graph kind of includes everything that we want to, we can look at this graph and say, okay, there is certainly a minimum right here. So I want to figure out exactly what that number is. Well, our calculator is able to do that. So if we hit second and then trace, then it pulls up a menu with a few options there. So then you're going to select whichever kind of value that we're trying to find. Obviously, well, maybe not obviously, but if it's not obvious, that's okay. That's why we're learning. But this is a minimum value, right? This is the lowest that our function goes. It is a dip. So we are going to hit the minimum button, and it is going to bring you to your picture of your graph. It is going to just bring you right back there with some stuff on the menu. So then what you're going to be doing is it is going to have a dot, like an X thing, that you're going to move along the graph. You can hit the left and right arrows to move this dot along the graph. And so you're going to choose a left endpoint, and then it is going to pull up another arrow, and you're going to hit the right button to move it over. And then you are going to then select what you're doing right there is selecting a right endpoint. And so what you do for those first 2 points that you choose is you are telling it, I want to find the minimum value between these 2 points. So it's kind of like before when I drew the box and said, we're only looking here. You, with your calculator, are telling it, I want to only look between these values. You're saying, find a minimum between these 2 points. Then it is going to ask for a guess, and it is going to start you over at your right endpoint, and then you're going to move over, and then you're going to guess just anywhere fairly close to your actual minimum value, and then you're going to hit enter, and it is going to work with your guess and look around it to try and figure out where your minimum value actually is. And it's going to do its fancy calculator stuff and use that to figure out approximately what the minimum value actually is, what that critical point is. And then once you hit your buttons and hit everything right here, it will spit out an X value at the bottom of that screen of the graph, and it will spit out an X value, and then it will spit out a Y value. And in this case, your calculator should say X is equal to 0 and your Y is equal to -1. Well, earlier when we did it manually on our own, we said this critical value is equal is 0, and then when you plug 0 into your function, you get -1, and our calculator was able to do that all on its own. So our calculators are very smart and able to do this on its own. So for in that sense, yes, your calculator is actually able to, from the graph, find minimum and maximum values for you. Now, obviously, you have to assist it with picking out, what about where on the function does that exist. But again, you don't have to start taking your derivative if you use this approach. So we have a few different approaches available to us right now. Well, there is another thing that the calculator is able to do, and that is our calculator is able to graph the derivative of a function, which is very crazy, I would say. It is not able to tell you what that function actually is, what the derivative actually is, but it is able to graph that derivative. And so our calculator, if you hit math and then go down in the list, you will find a button, an option that says in derivative. And that is a function that takes in three arguments. It takes in the function. It says take the derivative with respect to what, which for us will always be x. And then it says find the derivative at what number. So n derivative has the three options. You pick the function you want to take the derivative of. You always just hit x, And then you always just choose whatever number you want to take the derivative at. So let's say we want to graph the derivative of our function. We're going to let y1 equal whatever function that we want to consider. And then for y2, we want to use this inderivative. So we're going to go to our options and choose inderivative to pull this thing up. And then we're going to do y1 is the function we want to take the derivative of. And we want to, of course, we're doing y1 of x, comma, we're taking the derivative with respect to x. And here, what number are we going to plug in? Well, instead of it being a specific number, like 5 to -1, I want it to take the derivative at any possible input x. So now, with this setup, if I have y1 is equal to my function, and y2 is the inderivative of y1 comma x, it will graph the derivative of the function for us. It will not tell us what that derivative is, but it will at least graph it. Well, now some of you, if you're following along, your calculator did not pull up inderivative in these three options whenever you hit enter. Some of you, your calculator pulls up d over d blank of blank, and then a line at x equals blank. This is, again, weird notation, but it is going to be filled in almost the same way, just in a slightly different pattern. So this notation is, well, let's break it up into the pieces if we care about understanding it. If not, you can check out. But this says take the derivative with respect to what? Well, we're taking all of our derivatives with respect to x. Now, this box says take the derivative of what? Now, in our case, we want to take the derivative of y1. And then this last box is take the derivative with respect to the function, and then evaluate at what value. And so if we are, again, plugging this into graph, then we just want to plug in, sorry, then if we are wanting to graph this, we are going to just plug in x for that. But again, this is the same thing as when it has d over dx of f of x evaluated at x equals whatever number. So this is two different ways, depending on what calculator you have, that it will pull up our inderivative option. And so it ends for numerical. And so essentially the calculator does the fancy limit question that we're used to doing from our previous section. It finds the limit or finds a derivative using the limit at whatever point. So this is why graphing it takes a long time. But anyway, yes, those are some alternate options if we want to graph the derivative of our function. Now, you certainly can do that and then start trying to find mins and maxes that way. So hypothetically, I could give you this function up here, and then you graph the derivative, and then I say find mins and maxes for the derivative. Then you can look at your graph of the derivative and use the min and max options there. So yes, our calculator is able to lift a lot of the burden for this section for us as long as we're okay with graphing it and looking at our options in the graph. So it's actually very intuitive, very fancy, and very cool. Anyways, that is kind of where the end of how do we find mins and maxes and whatnot is. However, there's one last kind of question that we may run into in this section. So I can tell you to find, yeah, there's a clear button. I can tell you to find the maximum value of a function, but what if I told you f of x is equal to 3x cubed plus 2x minus 1, and I said find the most rapid rate of change, or where the function is increasing most rapidly. That second option is where you're going to see it worded the most. Well, what does it mean for a function to increase most rapidly? That just means the rate at which it is changing is the greatest. Well, the rate at which it is changing, we can just say is f prime. So we're really trying to maximize f prime as a horrible arrow. Essentially, all this question is saying is maximize the derivative. So to find where the function is increasing most rapidly, well, I can take this derivative, sure. This is f prime of x. We keep the 3 from the coefficient, but then the power rule says bring the 3 down, subtract 1 from the power. Derivative of 2x is 2. So this derivative is just 3 times 3 is 9, x squared plus 2. And now this is the function that we're trying to maximize. Now, I'm going to spoil this and say this is not a good example because this derivative, if we graph it, looks something like this. And if I said find the maximum value of this, you're going to say there is no maximum value, which is correct. So this is a little bit of a non-example, but I'm setting essentially, even in an example that was nice and good and clean, there was a maximum value that we could find, then, well, essentially the setup is the exact same way. Where is the function increasing most rapidly? That is just saying maximize the derivative. So take the derivative and now start from scratch, find the maximum of this function. So essentially the only added step is take a derivative and now work with that. Okay, and our practice exam does have a nice question with this as an example that is kind of intending us to use our calculator for there. So it's kind of combining the idea from the previous thing that I just talked about. Take a function and then use your calculator to graph the derivative, and then looking at the graphs, determine where any max and mins are. So from there, that is where this lesson ends. And I don't have a good closing. I didn't plan any kind of closing. I just planned lecture. Okay, goodbye.